Hello everyone. Today we're going to be looking at the vehicle dynamics and how one would size the engine or the electric motor if the vehicle is propelled by electrical machine. So we'll be looking at the characteristics of the electric machine in relation to those of the internal combustion engine. Right, so let's begin with the forces that act on a vehicle. Remember, the purpose of your powertrain or the internal combustion engine or the electric machine that propels the vehicle is to overcome all the other opposing forces, the simple physics, first year physics. All right. So now let us look at what are these forces or what is the load of a vehicle on the electric machine or the internal combustion engine. Right. So first of all, we are seeing that in an inclined surface, we have this gravitational component that is acting against the vehicle, the mg sine alpha. All right. So which it's normally called the gradient force, or the force due to the gradient, right? And then the other force is the one that's acting normal on the tires, and we can see that it's also influenced by the gravitational pull, and which means the weight or the mass of the vehicle. But as we can see, the higher the inclination or the gradient, the less the normal force on the tires, but the more the gradient force on the vehicle. All right, so that force is referred to as the rolling resistance force. Basically, it's the force whereby the tire refuses to roll. Initially, it sort of refuses to roll. It's not such an significant, but it's a function of the weight. The heavier the vehicle, the more the rolling resistance. The heavier the vehicle, the more the gradient force. Okay, now I've listed them here, that we have the traction force. The traction force is now the force that's propelling the vehicle forward. Okay, it's referred to as the traction force. And then we have the resistance force, we have the total mass, vehicle speed, mass factor, and all those components. All right, so the tractive force, right there, that component, it is the one now that needs to overcome all these resistance forces that are acting on the vehicle. All right, and if there's a difference between the tractive force and the rolling resistance forces and all these other forces that are opposing motion of the vehicle, there will be acceleration. Okay, there will be acceleration. And then if they are the same, if your tractive force, let me write it. If you have blob of mass, this is normal physics, you have a force, let's say this is the force that's opposing, we call it the resistance force, and then you have the tractive force. Okay, the point here is, if the two forces are the same, the blob of mass will not move, right? But if the tractive force is greater than the resistance forces, then you will have acceleration. Okay. Now, if you were running at a particular speed, and then the tractive force and the resistance forces become the same, then the vehicle will still be in motion but will not be accelerating, right? And that's what we call coasting, right? So I think this is just the basics in terms of the forces acting, and it is these forces now that your propelling component or propeller, such as a internal combustion engine, or where the source of propelling is coming from, or the tractive force is coming from, the internal combustion engine or the electric machine needs to overcome, or it's the one that actually is exerting this tractive force. All right. There's also what we refer to as the skin effect, and the force close to the skin of the vehicle, almost same speed as the vehicle, but the air further away from the vehicle, it of course moves at a slower speed compared to the vehicle, and then the difference between these two creates actually a friction All right, and that friction force is defined by this equation. Okay, and where it's a function of the speed of the air and the speed of the vehicle. Okay, so you can see the faster the vehicle, and the faster the air, and especially if the air is in opposition, this component will become greater. And the other parameters are really of the design of the vehicle, the shape of the vehicle in front, and so on. That's why you'll find that fast cars will have a different design, so that they really overcome this this air friction doesn't become a big component. All right. So that is the third additional force. Remember, we had gradient, we had rolling resistance. Now we have the because of the aerodynamics around the vehicle. So these are the forces trying to prevent motion. All right, and this is just a curve that illustrates this effect of the air. All right, so of course C representing a portion of the design of the vehicle, and as we can see, the dotted line, this line, we can see that when the vehicle when we look at it in terms of the vehicle speed and the engine power, you can see that for, let's say, 25 kilowatt, for this C 0.25, you have a higher, you can reach a higher maximum speed compared to the C of 0.32. This just shows you that because of the air resistance, there's more air resistance with C 0.32. The aerodynamics of the vehicle, there's more air resistance, and because of that air resistance, for the same engine, this vehicle cannot reach a higher speed compared to the one with low resistance, basically the shape of the vehicle. Right, and then here we don't really see this one. If we look at the 50 kilowatt, same logic, this one with this longer dashed lines also does not reach as much higher speed compared to the vehicle with the lowest resistance experience. And as you can see, this one has a bigger resistance, 0.4. So that's just a curve to show you that now for this vehicle, for example, with this kind of air resistance, 0.40 shape factor, to basically reach that speed of 175 kilometers per hour, this will have to be at 100. This vehicle with 0.04 will have to be at 175. Okay, yeah, 175. It has to be at 75 kilowatt. So you need a bigger engine, right? Just because of the aerodynamics of the shape of the vehicle. See, this is how impactful these forces are on the loading on the vehicle. All right. Now, going back to the vehicle dynamics, these are just the equations that describe the rolling resistance, for example, the gradient resistance, and as you can see, it's a function of the mass, the weight, and these two factors there that are probably functions of the characteristics of the tire and so on. And then back to that normal equation where you are saying the tractive force, the difference between the tractive force and the forces acting opposing motion on the vehicle, the loading, the weight, and so on. If there's a difference in that, there will be acceleration. Okay, because Ft is the tractive force. So which means on a road, one has to think about what is the typical gradient, what will be the maximum allowable gradient on our roads, first of all. And there's also concepts such as drive cycles, where you in terms of time, the drive cycle will be a certain profile in terms of speed on the y-axis, and of a particular, and sometimes these drive cycles will also have a gradient component, and based on that drive cycle, which could be a route from here, let's say, to Pretoria. So it will really show how the vehicle drove and the gradient along the road. And based on that, one could actually extract what's the maximum gradient. And based on that, you could now, you know the mass of the vehicle, the aerodynamics of the vehicle. One would know these forces. And let's say what's the maximum speed. Maybe the maximum speed is that person could drive is 140 kilometers per hour, and based on that speed you will also have the force, the maximum force due to the wind and so on, and maybe you get the typical wind speeds of the area and so on, and then that will basically give you more or less what one should anticipate to be the maximum forces. So which means you need now a combustion engine that can actually produce that force. All right, but that will just to be equalize the forces. So now to be able to accelerate, it means what you would have calculated for the these drag forces and so on would sort of be your minimum. You can't go below that. Your engine capacity can't be below that in terms of power, or yeah. And then looking at this, you'll find that as cars, sometimes they will be measured based on the acceleration, how much it can accelerate in a particular time. Right, and that right there, that gives you this component that you have a particular mass of the vehicle. What's the acceleration? All right, then, and that all, if you rearrange this equation, you have Ft equals to mv, I'll call it now acceleration, plus the drag forces in total. Okay, all the forces that are opposed. So for the vehicle to be able to accelerate, so you have this acceleration force, or force due to acceleration, Newton's law, first law, plus the maximum total forces that could be acting on the vehicle, which are the aerodynamics, the rolling resistance, the gradient, and so on. Right, so it means now one has to size the internal combustion engine based on these requirements. If let's say you want your vehicle to be able to accelerate from 0 to 100 kilometers per hour in 10 seconds, right, that is factored in this equation, in addition to the fact that it's not only acceleration that the vehicle needs to be should be able to do. It should be able to accelerate like that, and at the same time overcome the forces in spite of the forces that are acting on the vehicle. Okay, right. So now this is your engine propelling the vehicle, or the electric machine propelling the vehicle to perform in this way. However, there are other mechanical components that are linking your engine to the wheel. It's not a linear, it's not a direct connected system. You've heard of a transmission system, which consists of the gears and so on. So the question is now, how do we, all these forces we are talking about are at the wheel, Now how do we move from the wheel to the engine? Because there's losses and all that kind of stuff from the wheel to the engine. All right. Now, this is the propulsion power. Hold that thought. This is the propulsion power, which is your torque at the wheel, and the angular speed of the wheel. All right. Or in other way to represent this, it could be the force at the wheel and the linear speed, the linear speed of the vehicle, but as opposed to the angular speed of the tire. Okay, but how do we convert angular speed to the linear speed? That's the equation. So you have your wheel with a radius rotating at a particular speed, omega h wh. Okay, this writing is not nice. Knowing the radius of the wheel, you can convert to the linear speed. And you can already see that the bigger the radius, the more translational, for the same angular speed, you get actually, the vehicle can be made to move faster. And no wonder, again, sports cars have bigger radius of the tires of the wheels. Small cars, Picantos and so on, very small wheel radius because they are not fast cars. Okay, that's the reason. Anyway, that's a side topic. Okay, so now we have an electric, there's also a propulsion system that could have multiple gear, single gear ratio. It's also possible for electric vehicles, which is actually a desirable thing because a gearing system is heavy and it's an additional need for maintenance, for example, and it just increases the cost of the vehicle. All right, now let's go back to how do we move? The question now is, how do we take the power at the wheel? We've already know, we can calculate, we know what type of acceleration we want on the vehicle or we are designing for. We also know what are the forces acting on the vehicle, and now we know the tractive force that we need. But this is still at the wheel, and that's that tractive force. The tractive force times the radius gives you the torque, right? The tractive torque, okay, which is that tractive torque at the wheel. Okay, now how do we move from the wheel to the engine or the electric machine? All right, so now if we're looking at gears, basically gears either will change you have an input to the gear train and the output. In our case, the output is what we are experiencing at the wheel. Okay, the input, it's the propeller itself, the internal combustion engine or the electric machine. All right, now you are your input there could be, your engine generally will have higher rotating speeds compared to the output. So generally your omega 1 will be greater than omega 2, okay, because of the gears. But because omega 2 is less, you are actually able to increase T2, the tractive torque, okay, because of the conservation of energy. Or let's say if we assume the input power is the same as the output power, if omega 2 is less than omega 1, to balance these two inputs and output, it means the torque of the T2 will be higher than T1. And T1 will be less than T2, what else omega 1 is greater than omega 2. Okay, I think, simple math there. Right, now, but in reality, the gear train is not 100% efficient, okay? There's a particular efficiency of the gear train. Right, now, as I mentioned, omega 2 in our case is at the wheel. Omega 1 is your engine or propeller or the electric machine rotating speed. All right, now the gears are defined, we can really define the gear ratio based on that equation because again, law of conservation, omega 1 R1 is equals to omega 2 R2. All right, and right there we get your relationships with the torques, assuming that it's 100% efficiency. So basically you're saying T1 omega 1 equals to T2 omega 2, and then you play with the equations there. Right, so have this in mind. Now remember we said one is one our engine. I'll come back to this engine. Now coming back to this figure here, this figure now shows us that at lower speeds, this is the speed axis, kilometers, and then this is the attractive force. We can see at lower speeds you actually can achieve high torque. Gear number 1, then gear number 2. As you go higher in your gears, the tractive there's not much torque because you are now going at higher speeds, right? So here we see that omega 1. So remember that gear ratio is omega 1 over omega 2, the output. And we can see here that in the first instance, it's 3.3, which means because the gear ratios, your engine speed is still higher than the wheel speed. But at higher gears, gear number 5, we notice that your ratio now is less than 1, which means omega 2 is greater than omega 1. Okay. Remember the principle was as you have the box, you have your gearbox, T1, omega 1, T2, omega 2. As the speed increases, the torque will drop. Okay, and that's what we are noticing here, that now omega 1 at higher gears is less than omega 2. Okay, so which means omega 2, the torque at the output is now less because omega 2 is bigger. And this is the relationship we are seeing in this curve. Okay. Now, when we look at the engine as well, at almost zero speed, actually you don't have torque. There's not much torque, actually. The biggest torque you get at particular ref counts of the engine. That's when you get your peak torque. And that is why when you start your vehicle, it will have a particular ref count. It won't be zero. It will ref at a particular ref, either 1,000 RPM or something like that. And that's so that you are able to actually move in the region where there is torque. And that is one of the problems with the internal combustion engine, right? Let's first do some calculations. We said the force, tractive force at the wheel is equals to power output at the wheel. Right. Now, we want to incorporate the gear ratios and the fact that the vehicle may have gears. If it doesn't have gears, then the P out is actually just your P in and then simple calculations, because P in is T1 times omega 1, right? Which one? T1 omega 1. All right. Now, if we have a gear, right? If we have gears, now the gear ratio is defined by omega 1, omega 2 equals to R2 over R1. That's your gear ratios. It's like you. All right. Now, we play with the equations. P in, I'll write it in a different form, is equals to P out over the efficiency. Right. The efficiency, this is the efficiency of the gearing system, the efficiency of the transmission system as well. Okay. So P in is equals to P out over the efficiency. Remember, P out is at the wheel. Right. And then we said P out is the tractive force, which we already know. We can calculate P out times the radius of the wheel. Now those two gives us what? The torque at the wheel. Torque, okay. And this torque, remember, times the speed at the wheel equals to omega R omega divided by our efficiency times the wheel angular speed, right? The wheel angular speed. Okay. So this is the definition of the output power, right? If you multiply the tractive force at the wheel times the radius, as I indicated before, times the speed of the wheel, you get power. This whole gives you power, but still the output power. Okay. Now, the input power, remember we said the input power is tractive, but I will have to give it a new definition. At the, let's say, give it TE, which is the engine or the motor, times the engine speed, which we said was omega, right? So this is omega 2, this is omega 1, equals to Ft times omega times omega 2 over the efficiency, our TEM now equals to tractive force times radius of the wheel times omega 2 over omega 1 efficiency. Now what did we say? Omega 2, omega 1 over omega 2 is the gear ratio. Ft over efficiency times Nx. Right. Remember, we know the tractive force at the wheel. We know the radius of the wheel. We can assume the efficiency to some extent. We have the gear ratio. That translates to obtaining the tractive force at the shaft of the engine or of the electric machine. All right. So we were able to move from the tire to the engine or to the what level of torque is required at the engine or at the electric machine. Okay, so now if you look at the torque speed profile of the electric machine, it has a similar shape as we observed with the gears. Remember, with the gears, it was gear number 5, gear number 1. So we have that behavior already on just the characteristics of the electric machine. And that is why actually you don't actually necessarily need a gearbox. No need of a gearbox. Okay. Now, this is the speed. That's your torque. The other advantage is that at zero speed, you have torque. Your vehicle can receive torque at an instant of driving. You need to rev it to a particular, it has instant torque. Right. So that's the biggest advantage of the electric, one of the biggest advantages of electric motor for electric vehicle propulsion. Okay, now let me use a different color. If we look at the power curve, right? Remember, power is torque times your speed, right? If you remember here, the speed is increasing, but it's still constant, so we have a linear curve there. Now, because of this behavior, we also have a constant, because torque is going down, the speed is increasing. We now have a constant torque there. At some point, it really, this curve doesn't retain this nice shape, and then we also have a dip in the power. And then this region here is called the constant power speed range. And in electric vehicles, you want this constant speed power portion to be bigger, because it means you can reach higher speeds for the same power demand from your battery. Remember, what is powering your motor? You have an inverter, right? DC, AC there, and ultimately it's your energy source, finite energy source, either a battery. So if you have a very finite energy source, such that you don't want, when this portion here dips, because of the characteristics of the motor and so on, when that portion dips, it creates also a dip in your power, such that to actually retain this power, you need more additional power demand from your source. Right. So what we had obtained with your tractive force at the wheel, remember, we were now able to translate that to the power in at the motor side, right? That power rating, it's this point. So you rate the machine at this point, just before the torque starts to almost not collapse, but to decrease. That's the rating. That's how these machines are rated. When you say the power rating of this machine is this, they are talking about this point right there. And with a suitable drive, you will be able to retain that power for a certain duration of time. This region here is called the field weakening region, but that's a different concept altogether. Right. So this is how one moves from the wheel to the electric machine. And once you know the power rating of your machine, remember that's the output power. Then the question is, what's the efficiency of your machine? And once you know the efficiency, you should know the input power. And once you know the input power, boom, you know all the how to size the electrical, what should your electrical elements be. All right.